So in this section, I will introduce the contracting function and what's the influence of this contracting function on the recursive sequence and the existence of the fixed points. So let's first define the contracting function. The contracting function is a function that is defined by whatever was x and y belongs to I. There exists a c that belongs to 0, 1. It's a value that is between 0 and 1, strictly superior than 0 and strictly less than 1, such that whatever was x and y, the absolute value of f of x minus f of y is less than or equal to c times absolute value of x minus 1. So to prove that the function is a contracting function, we can try to find this inequality, or we can use the inequality of the finite increments, that is saying that there exists a positive constant c that belongs to 0, 1, such that whatever was x belongs to I, the absolute value of f prime of x is less than c. So we need only to prove this inequality to say that the function is a contracting function. So we consider here the function f of x equals 1/2 exponential minus x, and we have x belongs to r plus. I know that the exponential minus x, the whole function is defined on r, but I will consider x that belongs to r plus. Okay, I want to prove that the f is a contracting function, and I will use the inequality of finite increments. So I need the derivative of the function f, which is equal to 1 minus 1/2 exponential minus x, and then we will find the absolute value of the derivative, which is equal to 1/2 exponential minus x, because exponential is a positive value. Then I have, so I will try to find, so here we want to find c that belongs to 0, 1, such that the absolute value of f prime is less than the value c. So let's try to find this value. So first I will start from x that is superior or equal to 0. This means that minus x is less than or equal to 0. It means that exponential minus x is less than or equal to 1. Then I will multiply by 1/2, and this will imply that the whole expression will be less than or equal to 1/2. So let's consider the value c is 1/2. So here we prove that the function f is a contracting function. We move now to the theorem of the fixed point. So here in this theorem, we will see that if we have a contractive function and we have an interval, the domain is mapped to itself by this function, then the function f has a unique fixed point, and the sequence or the recursive sequence that is defined by this function is convergent and goes to that the fixed point. So first of all, we need this theorem. Most of the time we need it when we cannot find the fixed point, but we want to prove that this fixed point exists. So then, if we have a contracting function, we can also conclude that the recursive sequence is convergent to the fixed point. So to have this result, we need to, first of all, to prove that the function is a contractive function, and also we need to prove that the domain is mapped to itself. So let's take a look at this result. How can the contractive function and the interval that is mapped to itself imply that we have a unique fixed point and that the recursive sequence is convergent to the fixed point, and how can we find this inequality? So we said that the function f, we suppose that our function is contracting, is a contraction. We will suppose that the function is defined on I and that I is mapped to itself. So these are the 2 points that we have. And we want to prove that there exists a unique A that belongs to I, such that f of A equals to A. Also, we want to prove that if we have a recursive sequence, then the absolute value of un minus A will be less than c to the power of n absolute value of u0 minus A. And also we want to prove that the limit of un equals to A when n reaches plus infinity. So 3 points that we need to prove. One, the second point, this point, and the third point is this point. These 3 points are the result of a contraction plus an interval that is mapped to itself. So let's start with this first point. So we will create a function g of x equals to f of x minus x. Of course, g is defined on I, since f is defined on I. So this is what we want to prove, and we will start our proof. So here we will try to see the variation of the function g. So we have here so we can find the fixed point. So if we want to find the fixed point using the function g, we need to find a point A such that g of A is equal to 0. So this is what we want to prove. So let's start our proof with the derivative of the function. I want to see the variation table of this function. So g prime of x is equal to f prime of x minus 1. And since the function f is a contraction, this means that the absolute value of f prime of x is less than c, and c belongs to 0, 1. This means that the absolute value of f prime of x is less than c, strictly less than 1. It means that f prime of x is between 1 and minus 1. Implies f prime of x minus 1 is negative. So this proves that g prime is negative whatever was x in the domain. So if we want to draw the variation table of the function g prime, we will see that, let's consider I is the interval AB. So A and B, we have the g prime here, we found it's negative. It means that the function is going from g of A to g of B. Of course, g of A is f of A minus A, and g of B is f of B minus B. We said also that the interval I is mapped to itself, and this means that whatever was x in I, f of x will be in the interval AB. So, if x equals A, this means that f of A belongs to AB. And it means that f of A minus A is positive. Also, if we consider x equals B, so f of B belongs to AB. And then we can conclude that f of B minus B is negative. So here we can see that f of A minus A is a positive value. So f of A minus A is a positive value. And also f of B minus B is a negative value. So the function is going from positive value to a negative value. This means that there exists absolutely C that belongs to AB such that g of C equals 0. And since the function is strictly monotonic, This means that there exists a unique C that belongs to the interval AB such that g of c equals 0. G of c means that f of c minus c equals 0, and it means that f of c equals c. So here we prove that there exists a fixed point, a unique fixed point that belongs to AB of the function f. Let's move now to the second point, is that we need to prove that whatever was n superior than 0, the absolute value of un minus c is less than, let's say the fixed point is c, okay, is less than m to the power of n, absolute value of u0 minus c, and m belongs to 0, 1. Okay, so we know that the function f is a contraction. So this is what we want to prove. F is a contraction. It means that the absolute value of f of x minus f of y is less than m, absolute value of x minus y, whatever was x and y in the domain I, and of course there exists m that belongs to the open interval 0, 1. So if we consider x equals un and y equals a or c, the fixed point, this means that the absolute value of f of un minus f of c is less than m, absolute value of un minus c. And this, of course, equals to the absolute value of un plus 1 minus c. So here we have the absolute value of un plus 1 minus c is less than m, absolute value of un minus c. If we use the same inequality, so un minus c is also less than m times m, absolute value of un minus 1 minus c, which is m squared, the absolute value of un minus 1 minus c. So here, if we continue until we get the u0, we will get that m to the power of n plus 1 is times u0 minus c. So here we have the result that is proving this inequality, or you can use the proof by induction to prove this inequality, and it's also correct. We want now to prove that the limit of un when n reaches plus infinity is equal to the fixed point. So here I will use the inequality that I just proved, is that m to the power of n un u0 minus c. So here, if we want to find the limit of h1, we have here the limit of this when n reaches plus infinity, let's denote it L, is less than the limit of this when n reaches plus infinity. Of course, m here belongs to 0, 1. It means that the limit of m to the power of n when n reaches plus infinity will be 0. So the whole limit will be going to 0. And of course, this value is positive, so the limit will be positive. So here the limit of the absolute value of un minus c is between 0 and 0, which means that the limit of un equals c when n reaches plus infinity. So as a conclusion here, if S is a contraction plus f is defined on an interval that is mapped to itself, so we have first that exists a unique a belongs to I such that f of a equals a, so a is a fixed point. Second, whatever was n, the absolute value of un minus a is less than c, absolute value of u0 minus a, and here c belongs to 0, 1. And the third point is that the limit of un when n reaches plus infinity equals a.